So remember the final start from this material. So don't fall behind, try to follow with the lectures, try to ask questions. We don't really have a lot of time, right? Huh? Raise the final, what do you mean? Or am I going to write the final? Yes.
Are you sure?
The venue. You should always do, as a minimum, do the problems I did in class. Right? Because that's really what I expect from you. Whether I can ask that or not, that's another question. All right. So the answer, looking at the wave equations, this is plus 30x, so the propagation direction is negative x direction. This is in y direction, and I know E cross H is k. So I have x and y here, so I'm going to write x, y, z is pointing out. So the k is along the minus x, the e is along the y. So e equals h is k, so h must be going in. Going in is minus z direction. Looking at this number, this is omega, which is 2 pi f. So 2 pi f is 10 to the 9, and we did this a number of times already. 159.2 mega will make 10 to the 9. And k, this number is k is 30, k is 2 pi over lambda, so lambda is 2 pi over 30 meter. So it's converted to centimeter, you multiply by 100. Velocity, omega over k. Omega is 10 to the 9, k is 30. Right? These are the very basic things you should master, at least not have to worry about. Right? And everything built on this. Any questions? The follow-up question was the dielectric constant of this medium. And how do you do that? These are the things that you should know, right? The n is the square root of the dielectric constant, and that is c over the velocity. And c is 3 times 10 to the 8 meter per second. Velocity is 3.33 times 10 to the 7, right? And that gives you roughly 3 over 10, 3 over. It's like 0.9, like 90, roughly.
86.
Huh?
86.
Oh, this is 86?
Yeah.
Okay. So, and then wow. Really? And this is n. So to get the dielectric constant, you need to square it.
Absolutely.
That's a huge number. Any question?
That was epsilon. Okay. N is like 9.
Oh, 9.
Yeah.
Oh, okay. Well, that's what I was saying. Like,
epsilon.
this is like almost 9.
Epsilon is like 86.
Okay. All right. Any questions? Any question on any material? Yes. No. No. Yeah. Well, then that. Okay. Any questions? So we all good with polarization, circular polarizations, right? Okay. Please go back and do them. All right. So let's continue. Next module. So the next topic is adding a little bit complexity to what we were doing. Which is still in the same chapter in your book. I have a new chapter called Lossy Medium. So what we have done so far is to look at how the electromagnetic wave propagate in the medium, on the PCB, in air, or in water, or whatnot. Under the assumption there's no charge density, there's no current density in the medium, right? And it's a perfectly ideal medium. That means the amplitude of the wave, the signal would not attenuate. In reality, that's not true, right? So let's bring in any real material into our question. So now, if I have a block of, I say conductor, but loosely speaking, in the old days, when we define, that's how we define the resistivity or the resistance of the material, right? So if I apply a voltage across the material, has a cross-sectional area A, and it will set up an electric field along the material, and Ohm's law say V is IR. The voltage across it, if the electric field is E and uniform, then the voltage is just electric field times the distance, right? Because the voltage is E dot dL. If E is constant, it's just E times L. And the current is the current density times the cross-sectional area, right? This tells me how much current density I have moving in this medium. And the resistance is defined by the resistivity, intrinsic resistivity of the material times the length of this conductor divided by the cross-section, right? And then you cancel all this common factor, you come up to this. And this is basically Ohm's law in a vector form. And if I rewrite it, so J is equal to 1 over rho times E. 1 over rho, the rho is the intrinsic resistivity of the material. 1 over rho is called the conductivity of the material, right? It just, okay. This is the form that we usually use as Ohm's law in a differential form, in a vector form. Okay. And sigma is the conductivity, intrinsic conductivity of the material. We basically categorize the material based on this number. Is this a good conductor? Is it a good insulator? Is this a semiconductor? And so on, right? Now, but what we want to look at is this. What does this equation tells me? What does that tells me? It tells me if I have an electric field propagating in the material, I must have a current density because they come together. The electrons, the charge will respond to this electric field, right? So in the early statement where we say this is a source-free medium, rho, the charge density is 0, and the current density is 0, is no longer true when we're dealing with a real material because the current density cannot be 0. Why it can't be 0? Because we are propagating an electric field in it. If I have an electric field, I'm going to create this current density, right? So I cannot say there's no current density, but then I'm putting an electric field in the material. That just doesn't make sense. So we need to correct that, right? For any realistic material. So let's go back to our Maxwell equations again. Which is basically this, the differential form or the phasor form. Doesn't matter which one you look at. Now we say J cannot be 0, right? So let's look at this one. We say J cannot be 0, but instead it is proportional to electric field. So now if I put J and write it as sigma times E, I can rewrite it, just factorize it, EL, and then here I factorize it, J omega L. And then I say, wait a minute, this form looks very much like in the case where there's no source, where we say J is equal to 0 before. This is what we have, right? And from there, we have the wave equation, the differential equations. Now I'm looking at this and say, wait a minute, this looks very much like this. If I would redefine this as some kind of epsilon, we call it a complex epsilon. I just redefine the variable. And now this look the same, right? Which means whatever solutions that we come up with before still apply if I would change the definition of my epsilon. Are you with me? Right, okay. So what is this complex epsilon? This complex epsilon is equal to this, right? And because it's a complex number, because I have a J here, it's always a complex number. So we call this a complex permittivity, which has the real part is just epsilon. The imaginary part, 1 over J is minus J, right? So that's why this is always negative J. And the rest is just sigma over omega. The real part is called epsilon prime. The imaginary part is called epsilon double prime. This is a universal standard notation across different disciplines. So people actually do a lot of measurements in the earlier days to measure the permittivity of the material. They will get both number, epsilon prime and epsilon double prime. And from that, they can get this complex permittivity and so on. What do we use it for? I'm going to show you in a little bit, right? But so far it's okay. The only part that a lot of times, you know, as a student, as a beginners, you would be confused of is because there's so many epsilons, like which epsilon is what, right? So back in the original epsilon, what is this epsilon? This is the permittivity, which is the free space permittivity, 8.84 times 10 to the minus 12, times the relative dielectric constant, right? That's what we've been using in the past. And that's what epsilon is. But now when we write this as epsilon prime, epsilon double prime, what does that mean? Well, epsilon prime is a real part of the complex permittivity, which is exactly what we had before, epsilon times epsilon now, right? So epsilon and epsilon prime are the same. Epsilon double prime is nothing more than sigma over omega. Are you with me? Epsilon double prime is the imaginary part of this complex permittivity. But by itself, it's not an imaginary number, it's a real number, right? When I say 2 plus J, 4, 4 is a real number. Only when I put the J together, that becomes the imaginary number. So epsilon double prime is still a real number. Are we okay? And this is always epsilon prime minus epsilon double prime. There's no other cases. All right, so here's the definition. All right, what does that mean? So before we say, okay, now if my phasor equation was whatever it was that we just wrote, and combined with the other equation, we say we can write the electromagnetic field as a traveling wave, right? That's what our conclusion was. Now I can still do that, but I need to redefine the variables. When I put this together, now this is a complex permittivity. When I put that together, this is my constant of my differential equation. This differential equation tells me the electric field is a traveling wave, right? So I write the electric field as a traveling wave where K is a complex number, I say Kc. But I can rewrite this. I can rewrite this as e to the j omega t times e to the minus Kc dot r or times r, right? Right? Exponential. Okay. And because this is a complex number, I'm going to absorb this and call this gamma. So gamma is defined as JKC, where KC is defined as K is omega over velocity, so mu epsilon, where epsilon is the epsilon C. That's the KC. You don't have to remember all that. Those are just the definition we use in between. When we do calculation, we don't have to do that. So all in all, what I'm trying to tell you is this. If we are going to deal with real material where the current density cannot be zero, you absorb that conductivity terms into the electric field, into the permittivity. And so now you can write the wave, electromagnetic field is still a wave, but with a complex number. E to the j omega t is just the oscillation part. So if I'm writing the phasor, I don't need to worry about this part, right? It's always there. This is oscillating in time, always the same frequency. This is the part that we need to pay attention to. Gamma is what we call a propagation constant because it tells me how the wave propagates. And the propagation constant is a complex number. The real part is called alpha. The imaginary part is called beta. Alpha is called the attenuation constant. The beta is called a phase constant. I know a whole bunch of definitions, right? So I'm going to write one more step, and then hopefully we'll see what it means. So the electric field is equal to an amplitude and an angle and oscillation part. If I just want to expand this part, now I can write it as e to the minus alpha r, and then e to the minus j beta r. Beta is like k. So, right? This is what I mean when gamma is complex number can be written as, the real part and the imaginary part. So let's look at every single term. The first term only tells me it has an amplitude, it has a direction, the electric field, right? This term only tells me the electric field is oscillating in time with a fixed frequency, right? With the same frequency, then everything in the circuit oscillates in the same frequency. This one, what is this? E to the minus alpha r, what is it? This is your exponential decay term, right? Remember what is e to the minus x? If you would plot e to the minus x, what does that look like? Exponential decay. So this one tells me how fast the electric field amplitude will decay along the distance r, right? The longer the distance is traveled, the smaller the amplitude becomes. This one, what is this? This is nothing more than my omega t minus beta r or kr, right? This part together form the traveling wave, right? So what I'm trying to say is the solution, when you take the real parameter into account, the only thing that changed from what we learned before is that we have to have this term here, attenuation. That tells me how fast the signal will attenuate. Are you with me? Okay. So in this chapter, what we need to do is figure out how to calculate this alpha and beta. And that's it. The rest is still the same as what we had before. The three rules that we've been using still apply. Okay? All right. So before we move on, let's look at, we say the complex permittivity is epsilon prime minus j epsilon double prime, has a real part, has an imaginary part. So people define this something called a loss tangent. So what is a loss tangent? that means if I'm looking at this as a complex number, this is the real number, this is the imaginary number. The real part is epsilon prime, the imaginary part is epsilon double prime. Then this is my complex permittivity, and this phase angle is called delta, right? Then when I take a tangent of this angle, what do I have? Epsilon double prime over epsilon prime. That's how we define this, right? Okay. So lost tangent, nobody really care about this angle delta. Nobody would ever ask you what is the phase angle of delta. Nobody would ask you. People only care about the ratio of this epsilon double prime over epsilon prime. They call it lost tangent. People only care about the lost tangent. So do not break it up. Later on, when you see a delta, you know this delta is not the lost tangent delta. Okay. Lost tangent is including the tangent delta altogether. Okay, so I know epsilon prime is just the same as epsilon double prime is sigma over omega, so lost tangent is also sigma over omega epsilon. So what does lost tangent tells me? It basically tells me how lossy my material is. As a double E, you have to know this parameter. So when you have a circuit board, you design a circuit board, people ask you, well, what kind of circuit board do you use? It's not always FR4. FR4 is only for very low frequency, very low power, right? So, and there's like hundreds of different substrate that you can choose from. How are you going to choose them? This is one of the parameter you want to choose. Do you care about the loss? How high the frequency? It has a frequency in here, right? It has a frequency in here. So the higher the number of the loss tangent, the more lossy is a circuit. So if you want to design something with very low loss, your circuit board with very low loss, you want to pick a very small loss tangent. So these are the material, you can Google it, you can do a lot of things. This is one of the very common high frequency circuit board is called Alumila with an A, but it's aluminum oxide, Al2O3. It's a crystal, like creamy color, but it's a hard crystal, like glass. So the dielectric constant is roughly about 9.5 to 10. The loss tangent is 3 times 10 to the minus 4. So it's a pretty small number, right? So this is one of the very common substrate for high frequency circuit. Teflon. Teflon is the white plastic that we use in the coaxial cable. If you cut the better quality coaxial cable, some of them use nylon, right, which is cheaper. So Teflon also has a very low loss tangent. So people use Teflon a lot for high frequency circuit. And then there's something nylon is worse, but it's cheaper. The silicon, the water is terrible, right? 0.15 instead of 10 to the minus 4. I mean, that's a few order of magnitude difference, right? So you can specify, right? So as a double E, these two parameters you should know well because the dielectric constant dictate the size of your circuit. If you want the circuit to be smaller, your device to be smaller, you want to use a high dielectric constant material because then everything swing. The line length, the line width, everything swing according to the dielectric constant. And then if you want something that is very low loss, you want to pick something with very low loss tangent. All right, so pay attention to these two parameters when you are working. FR4 is not even here. No, it's not plastic glass.
It's like a compound material. It's like fiberglass reinforced.
Yeah, those are more, but some of the fiber would be here too, but it's not. Yes, that's more like a paper. FR4 is more like a paper.
You want to make circuit boards out of beeswax?
Huh?
Beeswax?
You can use yeah, glasses here. Anyway. Yes, different types of ceramic. There's so many different types of ceramic. We use a lot of ceramic because we have the ability to change the property of the ceramic to get different dielectric constants, to get different temperature coefficients, to get different loss tangents. So there's a whole science in this. Superconductivity is not really a ceramic per se, but we can talk about it, right? The structure is crystal, but you can make it more like a powder, like a pure. Okay. All right. So, but one thing I want you to pay attention, or one thing I want you to ask yourself. We just say loss tangent. The lower the number, the better it is, right? The lower the loss your circuit is, right? But I have a conductivity here, right? Electrical conductivity. So does that mean a low electric conductivity is lower loss and a good conductivity is worse? Do we contradict ourselves? What do we mean? We can answer that. Why do we say low conductivity is good? Isn't good conductivity is a good conductor? Yeah. One, going once, going twice. So what are we talking about here? We are talking about we have a medium and we are sending an electromagnetic wave through it, right? What we're saying is if this medium is a good conductor, that's bad news because the electromagnetic field cannot penetrate into it, right? Electric field is zero, magnetic field is zero inside a good conductor, right? It'll stop right at the surface. So the better the conductor is, the shorter the distance the electromagnetic wave can penetrate into it, right? So the loss here, when we say, well, the circuit has very high loss, the loss is not from the ohmic loss. It's not the conduction loss that we used to think. I'm using, because we always use the best metal, either gold, silver, copper, right? We hardly use anything else for the transmission line. So the ohmic loss is already very small. But remember what we say, when I have a printed circuit, a PC board, if I have a circuit on top, right? This is the trace. Where is the energy of the signal? Right? We talked about that before. Where is the signal? Where is the energy stored? Is that on the trace? No. Faraday's law tells me the magnetic field is going around the wire, right? The energy is in the material, in the dielectric material. So energy loss is not the energy, the ohmic loss on the trace. That's very little. Yeah, there's some, but very little. But most of the energy is lost here in the dielectric. We call it dielectric loss. Not ohmic loss, not the conduction loss. Right? Most of the energy loss in the dielectric. That's why we need to pick a dielectric material that has very low loss tangent. Right? Now we start getting into something a little bit non-conventional thinking. All right, so to do the math, so this definition is going to be on the cheat sheet. So let's see how we use it. We say gamma is JKC, and this is what KC is, right? K is basically omega over velocity, and velocity is square root of mu epsilon, and that's basically what this is, right? Okay. And then we say, and we can write gamma as alpha plus j beta, and then we can also write the epsilon, complex epsilon as epsilon times 1 minus j epsilon double prime over epsilon prime, because, right, we did that. C is equal to epsilon prime minus j epsilon double prime. So this is just nothing more than epsilon c, right? And then we say epsilon double prime is j over omega, epsilon prime is the same epsilon, so all this definition are the same. And we also say epsilon double prime over epsilon prime is what we call loss tangent. So all this equation, all these definitions are the same. Depends on what is given, then, right? And you can relate them. For example, I can relate this and say, looking at this two, I know loss tangent is the same as sigma over omega epsilon. Or looking at this two, I know loss tangent is epsilon double prime over epsilon prime, right? So all those definitions are in here. So get used to knowing these expressions and find the equation you need to solve your problem, right? I will not define each term separately. This is it. You need to learn to use it. All right. So we already did this. We say this is attenuation. This is the oscillations. And so what does that mean when I have a complex permittivity? That means this is the same. This is the oscillation part. That means the electric field or the magnetic field still oscillating. But then the amplitude would decay exponentially, like this. For ideal oscillation, the electric field amplitude would stay the same. Doesn't matter how far do I propagate in the material. But if the material is lossy, then the amplitude will decay exponentially fast, right? So before, we didn't talk about dB scale, did we? Before we move on, I want to remind you what dB scale is. So in your freshman physics course, I'm sure you have done some experiments that you have to plot the data. And if the data has a wide range of order of magnitude, then we use a log scale, right? That's the reason we use a log scale, because then we can have different order of magnitude and still be able to see the details of the function, right? Okay. Now, here we have an exponential function. That means the amplitude will change drastically, right, over many order of magnitude. So when people talk about wave, very likely we use dB scale. So I want to remind you what dB scale is and how to use it. dB scale, we first learned in acoustic wave, sound wave, is defined as 10 log base 10 of the ratio of the intensity, right? For the sound, this is the minimum intensity of the sound that most people can hear over the sound that we are listening now. For us as WE, is a ratio of the power. It could be the input power versus the output power, for example, right? So it's a ratio of the power. Now, power is proportional to the square of velocity of the voltage or the square of the current. So if you're looking at the voltage amplitude instead of power, then you need to multiply by 2 because the 2 will bring it in front of the, right, in the log scale. That becomes 20. Okay. So remember this. This is very often is even for working engineer without a calculator, a lot of engineer will still answer wrong, right? So a lot of people will say, do I multiply by 10 or do I multiply by 20? This question come up a lot. I hope you will know how to answer it in your interview. Now, this is a log number. So if this number is greater than 1, right, log of a number that's greater than 1, then this number is positive. If you take a log number is less than 1, then this is negative, right? Because the log looks like this. 1 is right here, right? Above it is positive, below it is negative. Okay. So what does that mean to us? So for double E, we are comparing, for example, the output power over the input power. If this is greater than 1, that means I have a gain, right? Most likely I have like an amplifier. If this is, sorry, if the ratio is less than 1, that means this dB is negative dB, then I have loss, like going through a filter, attenuator, and ones. Okay. So just some something for you to play with in your free time. So someone told me once that a good engineer should have an order of magnitude on your fingertips, like without reaching out to a calculator. For example, if I tell you, oh, the room is very big, but how big is that? Well, it's like 1 meter by 2 meter. Is that big? Is that, I don't know, it's 1 meter by 2 meter. I don't know how big is 1 meter. You have no concept. You're not a good engineer in that scale. So if I tell you, oh, I have an amplifier, it's really cool. I put out like 3 dB of power, 3 dB of gain. Is 3 dB good? I don't know, right? 3 dB is only double the power. It's actually not very good. Okay. But if I tell you my amplifier is like 50 dB gain, wow, that's huge. How big is 50? Why is that huge? Am I willing to pay more? How much more? So a few numbers for you to remember. If you have take a log of base 10 of 2, this is roughly about 0.3. You multiply by 10 is 3. So 3 dB, you hear 3 dB a lot. A lot of people say, where's the 3 dB point? Where's the 3 dB? Well, what is 3 dB? 3 dB is a half power point. I mean, double the power, right? But if you have 1/2 is 2 to the -1. The -1 move in front of the log, that becomes -3 dB. So -3 dB is half, plus 3 dB is double. Are you with me? Trust me, boy, you can check it with your calculator later. Right? But 3 dB, you hear that a lot, a lot. And then the next one is 10 dB. So what is log base 10 of 10? 1. Right? 1 times 10 is 10. So 10 dB means 10 times. If I want to say 100 times, 100 is 10 to the second power. This is 2 times log 10, right? So 20 dB. So it's very easy to read this. So if I have 20 dB, how big is 20 dB? You drop the last 0 and raise it to 10, 10 to the second. So if I have a 50 dB gain of amplifier, how much amplification do I have? Drop the last 0, raise it to 10, 10 to the 5th, 100,000 times. Right? We have 100,000 times the gain. That's huge. That I'm willing to pay some money. Right? Okay. So, and for those who like math, you can get a rough idea of a lot of numbers. So for example, what is -9 dB means? I don't know. So I know -3 dB means half. So -3, -3, -3, that would give me 9 dB. So that means half of half of half, 1/8. -9 dB means 1/8. Try one more time. 7 dB was 7 dB. 7 dB I can think of is 10 dB minus 3 dB. What is 10 dB? 10 times. What is minus 3 dB? 1/2. So 10 times 1/2, 5 times. Right? So without the calculator, you can get to, very close what the power is supposed to be. Of course, you can always use a calculator for your exam, and you don't have to learn this unless people ask you that in your interview. If I interview you, I will ask you that. I want to emphasize one thing though. dB is a scale. dB is not a unit. dB is like 100 times, 1,000 times, a dozen. It's not a unit. Okay? It's a scale. But we can turn it into a scale if I use a standard reference. So there are two references, but for us, most of us work with small power, right? Our phone is only put out like 0.7, 0.8 watts, very low power. So if I use 1 milliwatt as a reference, this dB is called dBm. Now this is a real unit of power. Real unit of power. So let's see what does that mean. So what is 21 dBm means? 21 dBm means 30 dBm minus 9, which is minus 3, minus 3, minus 3 dB, right? 30 dBm, how big is 30 dBm? Again, I drop the 0, raise it to 10. There's 1,000 milliwatts. So this is 1 watt. 30 dBm is 1 watt, is 1,000 milliwatts. And then minus 3 is 1/2, 1/2, 1/2. So multiply together 1/8 of a watt, 0.125 watts. You can play with this. The number is here. If you try it and didn't get it, come see me. Okay. You don't need this for the exam. You might need it for your interview. Want to do before we do examples. So we say the electric field would have a attenuation term and then the oscillation term, right? So if I define the attenuation of the wave, attenuation, in dB, okay. So what does that mean? That means I'm taking the electric field at some distance r divided by the electric field at the origin, at some reference point, I call it origin. And then take the log and multiply by 20, that will give me dB, right? Why 20 here? Because this is electric field, this is not power. The power is proportional to the electric field amplitude square or the magnetic field amplitude square, right? Like V square or I square. Okay. So what is the magnitude of the electric field at some distance r? Well, I look at it, I have, this is a constant, so we cancel from the top and bottom. So I only have e to the alpha r, and when r is equal to 0, that becomes 1. And this is the phase. What's the amplitude of the phase? What's the amplitude of this? 1. This is a unit circle of just a phase, right? Okay. So the ratio of the magnitude is just e to the minus alpha r, and this is log base 10. How do you do log base 10 of e to a function? Remember, you can change the base, right, of the log by using this, like b, a, and then any intermediate base. I'm going to change everything to ln, so ln of e, that just becomes alpha r times 20. So, and then in the bottom, I have ln of 10, right? Because this is base 10. You can go back and redo this yourself and try to understand it better. So when I say attenuation, a lot of times I change it to a positive number just because attenuation, the word attenuation already implies is a loss of amplitude. So I don't need to double count the negative. Some people don't. Some people like to keep the negative. I'm okay with it in this case. If you want to leave it, I'm not going to take points off. But most people would just change it to a positive number. 20 over log 10. If you put in the calculator, you get 8.686 roughly, this number. Right. And this is a very useful formula to remember. Let me repeat that. If I want to know the attenuation in dB, that's just equal to 8.686 times the attenuation constant in number. This attenuation constant I get from the wave equation. Okay. Times the distance is traveled. Of course, different distance will give me different attenuation. Right, so 8.686 is the one that we use a lot. I'm going to put this in the cheat sheet, but whether this is dB per meter or dB, they're the same. You have to know how to use it. All right. So I think we are ready for the. Oh no, we're not ready. Okay, we're ready for the first case. Now, this is the example we have. This is the equation we have, right? For the propagation constant. In general, this is a complex number. Now, someone asked me on Discord, can we always use the generalized formula and instead of breaking down into different cases? Yes, you can. But there are two things I have against them. One is you just plug in equation, maybe your calculator can do complex calculation. You're losing the intuition that you're supposed to learn, right? So I don't recommend it. The second part is a complex number calculation, complex over complex, square root of a complex. If you make a mistake, you have no way to recover it, right? So, but I leave it to you, right? I don't recommend it, but that doesn't mean you guys won't do it. All right, so I want to look at this in two different cases. One is what we call the low loss dielectric. Why do I want to deal with this case? Because most of the time we want to use a material, like for a circuit board and a PC board, always low loss. We don't want to pick something high loss, right? So we use this a lot. Most of the time it's low loss dielectric. So I want to know how to deal with it. Okay, so what does that mean by low loss? That means my imaginary part of epsilon is much, much less than the real part. Remember what loss tangent is? Epsilon double prime over epsilon prime. That means this number is very small. How small is small? Well, we'll say for the argument's sake, we say if this is less than 1 over 100, we call it low loss, right? If it's greater than that, then we don't call it low loss. But this is not a digital function. It's not like 1% is low loss, 1.1% is not low loss. It's not like that, right? It's like the smaller the number, the better this approximation is going to be. We did talk about the binomial expansion, remember, right? We use that a lot, and this is one of the reasons we demand a 1% because that would be a good approximation for it. So what does that mean? That means when I'm looking at this form, I'm using the original form, right? I have a square root and I have a complex number here. Pretty complicated. Okay. But if I remember what the binomial expansion is, 1 plus x to the n is 1 plus nx, if x is small. How small? 1% is very small or less, right? This is a very good approximation already. So if this is small, 1% or lower, I can rewrite the square root to minus 1/2 in power, right? Now I have this form, 1 plus x to the n, where n is small. So I just rewrite it as 1 plus nx, so which is 1 minus 1/2 times this, right? Just using this formula. Very powerful formula, very simple binomial expansion. So now, and this gamma is equal to my alpha and beta. That means if I match the real part and real part, imaginary part and the imaginary part, I know what alpha and betas are. And that's what I need for me to write the electromagnetic field. Right? So let's see what is alpha. Are we doing okay so far? Or is that too much? Too much material in one day. We only have a few weeks left. Hang on. So the real part, what is the real part? I have a j here, I have a j here. So if I multiply this with this, I get the real part, correct? J times j is -1, right? So that means when I multiply it, I get this, and that is equal to my alpha. Okay, again, what is epsilon double prime over epsilon prime? That's the same as sigma over omega epsilon. And now I have an epsilon here, I have an epsilon here, they cancel, so I have sigma over 2 times this. Right. If you're interested, if you go back and rewrite this definition yourself, fill in the steps that I skip, whatever algebra you need. And you will learn a lot by redoing it. But wait a minute, what is this? This is my eta. Right, let's look at the eta. Eta is mu over epsilon, but this is a complex epsilon, so I have to write it like this, and which means the square root becomes -1/2 of this. I use the same binomial expansion, so that becomes this. Here, there's nothing else I can do. If this is small, I can just drop this and just keep this term. So that means eta still stayed the same as before, right? This is the wave impedance that tells you how likely, how easy can you propagate a wave in this medium, right? What is eta naught? Anyone? 377 ohms, right? Remember this. That is the wave impedance in free space in air. Yeah. So I can also write this as sigma over 2 times eta. That's my alpha. Okay. What is beta? Beta is the imaginary part of this. So what's the imaginary part? I already have a j here. So that means I multiply by 1. This is my beta. This is my j beta. So what is beta? It's just omega square root of mu epsilon. What is square root mu epsilon? 1 over velocity of, yeah. So this is just omega over velocity. This is nothing more than what we had before. The velocity is omega over k. K is the same as beta in our case, right? Wave number. So let me summarize this before I do a quick example. What we're saying is this. If I'm dealing with a lossy medium, how do I know it's a lossy medium? Every time I see any of this term, epsilon prime, epsilon double prime, see a conductivity in the problem, see a loss tangent in the problem, you know you're dealing with lossy medium. The first step you do is to calculate loss tangent and see whether this is less than 1 over 100 or the other limit, right? If it's less than 1 over 100, you know this is low loss medium. Right away, you say alpha is equal to sigma over 2 times eta, and beta is the same. Beta is my k, which is omega over the velocity. Nothing changed. The only thing that is new is we have an alpha term, attenuation term. Are we okay? So far, so good? Everything else stayed the same. Any questions? All right, so let's do an example.
We still have to find beta though, right?
Beta is the same as what we had before. So I need to know the velocity, I need to know the dielectric material.
So all you need to do is go through this derivation for alpha, basically.
Yeah, we only add alpha. So let's try this. Electric field at the origin has an amplitude of 1 volt per meter along the y-axis. And the wave function is given by this. The permittivity is given by this. This is the complex, of course, right? I want to find H. Okay. Again, all the problem is I give you E, you tell me H, I give you H, you tell me E. Okay. So now, when I see this, what does that tell me? I have a complex number here, so that means the permittivity is complex. I'm dealing with lossy medium. So the first step is I know I'm dealing with lossy medium. And so the next thing is I want to calculate loss tangent. But how do I calculate loss tangent? This is epsilon over epsilon, double prime over epsilon prime is the same as sigma over omega epsilon. Now here I already know epsilon and epsilon prime and double prime. I don't know sigma. I don't know the conductivity. It's not mentioned in this problem, right? So right away, I know what is epsilon double prime is 0.02 times epsilon naught. I know the epsilon naught cancel, but I want to tell you the epsilon double prime is include the epsilon naught. Epsilon prime is 4, which is the relative dielectric constant, times epsilon naught. Of course, this cancel. And this is 1 over 200, so 0.005, right? Less than 1%, so I know this is low loss. That's the first thing you need to establish. Is a lossy medium, is there a low loss? Okay. If it's a low loss, then you go to the formula. We have a formula sheet. I gave you a formula sheet, something like this. We'll go over that again. So the formula, I look up the formula sheet and say, hey, low loss, everything is the same. The only thing I need to calculate is alpha, which is sigma over 2 times eta, right? But sigma is not given. It's not given in the problem. What do? Oh, but sigma is here. Because I already know what loss tangent is, I can find sigma, right? Are you with me? So from here, I can write sigma is omega times epsilon times the loss tangent. What is omega? Do I know omega?
You can find it. You know K and you know.
I know K. Do I know V? All right, let's try it. What is this velocity? C over N, right? What is N?
Square root of epsilon.
Square root of the dielectric constant. So this is 1.5 times 10 to the 8. Right, that's my velocity. So I have K, what is my K? Beta, okay. 30, 15, so this is what? 15 times square root 5, right? Because this is 15 2x minus c. 15 times this, the amplitude of this is 5, square root 5. right? So I know that, so do I know omega? Yeah, I know omega. What is omega? Velocity is omega over k. So omega is k times v, which is this times this, which is, does anyone has a calculator can help me really fast? 15 times square root 5 times 1.5.
No, that's a big number. About 5, 10, 10 to the
5 times 10 to the what?
9. Right. Yeah,
Including the 10 to the 8? No.
did I miss
1.5 times 10 to the 8.
times 15 root 5?
1.5 times 15 square root 5 is what?
Oh, just not, that is including the
What? What yeah?
so
Doesn't make sense. Huh? V times K? 1.5 times this one. Okay, fine. I trust you. Yeah. All right, so I know omega is 5 times 10 to the 9. What is epsilon? That's my epsilon naught, epsilon out, right? Which is 4. This is epsilon out times epsilon naught, which is 8.84 times 10 to the minus 12. Times the loss tangent is 0.005. So all together, please. And then eta, what is eta? Is eta naught divided by the line electric constants, 377 divided by square root 4, which is 2, which is 180, 88, 89, fine. Right, so alpha is, what is it?
across the second row, so I got 8.85, 7 minus 3,
Times 10 to what?
minus 4.
Okay, so alpha is equal to 8.8 times 10 to the minus 4 divided by 2 times 189. What is alpha equal to?
Point 083.
0.08?
3. 083.
Just say 0.08. Yeah, fine. Right? And that's it. Now we are ready to write the wave. How do I do that? Well, just use what we learned last time before. Okay, so let's do that. I want to write H has the dimensions, has direction, amplitude, and then copy the wave part, which is sine omega t, which is 5 times 10 to the 9t, plus 30x minus 15c, right? So the direction first, what's the direction? Well, k is, I have an x and z here, 2 unit on the x, 1 unit on the minus z. No, sorry, it's 2 unit on the minus x, 1 unit on the positive z. So this is my k, 2 to 1, right? Y is into the page. So, and the electric field is along the y direction. So the E field is into the page. What's the direction of H? E is into the page. K is my thumb, so 1, 2, 3, 4 quadrant. Which one? 3? 1?
E.
The bottom one, right? H. So K is 2-1 ratio, then H is 1-2 ratio. So what does 1-2 ratio means? Minus X hat minus 2Z hat over square root of 5. Right? This is 2-to-1 ratio. Then the bottom one is 1-to-2 ratio. They're perpendicular, so it's reciprocal. 1-2 becomes 2-1. Okay. The only thing left is the amplitude. How do I find the amplitude? I'm going to take this part off. Okay, how do I find the amplitude? Eta.
Already found it, right?
Eta, 190, right? So E naught over H naught is eta. Eta is 189. So what is H naught? E naught, which is 1 volt, over eta, which is 189, which is, can you tell me what this is?
Just write it as that. 5.3 times 10 minus
5.3 milliamp per meter, right? So this is 5.3 milliamp per meter. But wait, we're not done yet. Why? Because we're doing with lossy medium, we have to have a e to the minus alpha outer. Alpha is here. We just put the alpha in here. But how do I handle the R? What does R mean here? Right? We come back to this point again, but let me tell you what to do just right now. Right? We'll come back and explain to you why we can do that later. So remember what K dot R? This is K dot R, right? So K dot R, so that means the magnitude of K hat dot R. That's what this term is. Same thing here, instead of KR is alpha R. So what we want to do is write this as e to the minus. I'm going to tell you what to do, and then I'll explain to you why next time. So e to the minus alpha R, I can write e to the minus alpha is 0.083. And what do I do with the R? This is the K hat without the hat. K hat without the hat. So what is my K hat? This is my K. My K hat is 2-to-1 ratio, right? Minus 2x hat plus Z hat, normalize it to 5. This is my K hat. K hat without the hat, so I put minus 2x plus Z over 5 here. Summarize it really fast. First of all, you need to know you're working with lossy medium. How do I know? When I see any terms like the complex epsilon, the conductivity, the skin depth, any of those terms in the problem, then you know you're dealing with a lossy medium. Immediately, you want to find out, are you in a low loss region? How do you do that? Take the loss tangent. Calculate the loss tangent. If it's less than 1%, good, low loss. Then look up the formula. All you have to do is to calculate alpha, the attenuation, right? So you calculate alpha. And the rest is the same. You just use the 3 rules to construct the H field, the direction, the amplitude, the wave. And the only terms you have to add on is this attenuation term, right? The alpha is what you calculate, and this R is your K hat without the hat. Square root of 5. Oh. Where would it fall?
How does this thing have an amplitude of 1 volt at the origin?
Oh,
If it's a sine function.
there's a sign?
Yeah.
Or not, this is one time sign.
But it's at the origin, so everything's zero. Right? And it's D.
D is.
It's. See what I'm saying? Wait, so.
Alpha is equal to sigma over 2 times A. Because it's a low loss, you're looking up the formula. So you have to get sigma. How do you get sigma? Because you know the loss tangent, and that is sigma over this. So we can calculate sigma here. What is eta? Eta is eta naught divided by that. Yeah, you calculate that, you get alpha. Try it, yeah, try it, yeah.
So
Yeah.
looking at this epsilon complex.
Yeah.
If I have a, well, I was talking about the DC. I got it. We'll probably do it. We'll talk about DC. But if I talk about DC, biggest is zero, this is it doesn't make sense.
If it's DC, then you're from the system. Okay. Yeah, here.
We go to A, to A and from here. We always do the solution.
And sigma would be.
Why didn't we do that in here?